Welcome to Study Loop.
Hello everyone, today we're doing chapter 23, problem 66, and this problem asks us to synthesize each of these compounds from cyclohexanone and organic halides having less than 4 carbons. And we can use any other inorganic reagent. So let's start with A, so we'll start with cyclohexanone. And we need to try to get an methoxide to this position. So something very simple that we can do to add this on at this position here is we can simply add in a halide such that we can get halogenation at this position. And so what we need to do is first make this into an electrophile, this carbon, these alpha carbons here into electrophile. And after we make it into electrophile, we can add some sort of nucleophilic moiety that composes of this methoxide to get product A. So if we add Br2 in acidic conditions, in, for example, acetic acid, we will get halogenation at the alpha carbon. Now that we have halogenation at the alpha carbon, we can use sodium methoxide to act as a nucleophile with a negatively charged oxygen to go through an SN2 nucleophilic attack to replace that bromine with the methoxide to give us product A. And now for B, we can start with, once again, the cyclohexanone. And now we can just add this as a straight chain alkane. So in step 1, if we use a base with deprotonates an alpha proton, we would make this into a strong nucleophile, this carbon into a strong nucleophile. So for example, I can use LDA, and then in step 2, I'll just add the alkyl group I want. So I'll make this into an alkyl halide such that this carbanion nucleophile can do backside 180-degree attack at this carbon, electrophilic carbon center, to get my substitution product for B. And now, once I have that for B, you also notice that we're reducing this carbonyl carbon or carbonyl oxygen to a secondary alcohol. So what you can use there is some sort of reducing agent such as lithium aluminum hydride and water that will reduce your carbonyl group to an alcohol. Just like this. And now for C, what we can do is, so we have two different substituents on both alpha carbons. So we can add them sequentially. So for C, let's start from the left side. So for C, we'll start with the cyclohexanone. And once again, we'll use our LDA. And then we'll have alkyl halide, and then we will get alkylation at one of these alpha carbons. And now if I use LDA again, because it's large and bulky, it's going to rip off the alpha proton at the least sterically hindered side. So it's going to rip off the proton on the right side. So I use LDA again, it's going to rip off that right side alpha proton, and then I can add my alkyl halide to get alkylation at that carbon center. And now we get product C. So now let's see for D. So for D, we're adding an alkyl group, but this is not the alpha position. So let's see, what we have to do is we actually need to make a organometallic reagent such that we can add these two carbons, ethyl group, across a double bond. So we know, for example, in A, we were able to get halogenation here, and then if I use some sort of elimination reagents, we can get a double bond going across these two carbons, and then we can add some sort of organometallic reagent to add these two carbons onto that double bond. So for D, we're going to start with the same thing for A. We'll have our cyclohexanone and diatomic bromine in acidic conditions. And then you'll get halogenation at the alpha position. And then if you use some sort of elimination reagents like lithium bromide and DMF, you will get elimination occurring to get a pi bond here. And now you need to make an organometallic reagent. So if I add those two carbons with bromine, and then I add two equivalent lithium, and then 0.5 equivalent copper iodide, then we will get CuLi, something like this. And then if this is step 1, step 2, I have water, then we'll get addition of these two, of this R group, onto your double bond. And in the process, your double bond is actually reduced into a straight chain alkane. This actually formates product D. So now let's see for G. Well, G, we're once again adding two substituents to two alpha carbons, so just like in C, but then we gotta add, in A, we gotta brominate one of these alpha positions, and then we need to reduce it, or eliminate it to get that alkene double bond. So let's start for E. This is E. So we'll start with our cyclohexanone. And we'll say, just to save some space, we can say that we're going to do LDA and then to our alkyl halide, and then this entire thing times 2. So this entire thing times 2, and then what you're going to get is your alkylation at both alpha carbons being the same group to get this product. And at which point, if we halogenate one of these alpha positions, we will brominate one of them, and that will make it for a good leaving group. And you have bromination at one side, and that will make for a good leaving group for when you want to add your eliminating reagents, such as lithium cobalt trioxide with lithium bromide and DMF. And you'll get elimination, so you get a tertiary alkene. And product E. And now for F, what you want to do is you need to now add one substituent to one alpha carbon, and then add the second substituent to the same alpha carbon. So you need to use a base that will favor thermodynamic enolate and not the kinetic enolate. So we cannot no longer use LDA for F. We need to use a smaller base that will favor the thermodynamic enolate, such that we can get the second alkyl group added to the same carbon that we added the first alkyl group, and then we can brominate on the least hindered side, and then we can eliminate that using the same reagents as in E and D. So let's start for F. Starting with cyclohexanone. Then we're going to use sodium methoxide with our alkyl halide to form one substitution, but then we're going to repeat the exact same reagents, sodium methoxide with this alkyl halide, to get the second halide, or second alkyl group attached on the same carbon. The reason for that is because it generates the thermodynamic product. at which point we can then brominate, and bromination will favor the least sterically hindered side due to the steric bulk on the right side. So we'll brominate the left side. And then we can just easily eliminate that with to form the elimination product for F.